So this is I know it's an old joke. I thought I'd put it up there because we're going to be covering memory operations in more detail now. So last time, if you remember, we had referred to something called the base address register, which is the R1 from this LDR instruction, the one in square brackets. So that's the register that has the actual address that you want to operate on. So it's called the base address register. It can be any one of these values, R0 through R12, the stack pointer, or the link register. So the earlier example was something we call pre-indexing, where you just have the register followed by an offset, and the offset can be 0 or it can be left out, but essentially it takes that offset, adds it to the base address, and then uses the resulting address for the operation, whether it's a load or a store. There's two more addressing modes. It's called pre-index with write-back. And the difference here is you put an exclamation at the end of the square brackets. So all that means is take the newly calculated address and store it back into the base address register. So here Rn is representing the base address register. When you add the offset after the load or store operation, the register will contain the new value with the base address plus the offset. Similarly, there's something called post-indexing, and this actually, you'll see the difference in a minute, but it calculates the address again, followed by an offset, but the offset you specify outside the square brackets, and it stores the calculated address back into, this is similar to pre-index with write-back. The only difference is the offset is put outside and there is no exclamation point. So here's an example. So for example, if this is pre-index with write-back, so if you do LDR R0 and in square brackets R1 comma immediate value of 2, it adds 2 to R1 and stores it into stores the value at that address into R0, and then it also updates R1 with R1 the address plus 2. Similarly, you can also include barrel shifts in your addressing operation. So you can calculate an address using the barrel shifter. Chances are it will be a nice even number, power of 2. So, and you can update the register again this way. So you can do a lot of things in one instruction. Essentially, it gives you this sort of code optimization, code size. Pre-index, which we've already seen before, is as it's always been, where you just add the offset and you don't write the address back into the base address register. You can also do the shifting here, which we may not have seen yet, but it'll do the same thing, but it'll use the calculated value, but it won't write that value back into base address register. Post-index, as you can see, does the same thing as pre-index with write-back, but here you specify the offset outside the square brackets and followed by a column. So should be pretty straightforward. Any questions? Okay. Now the store is the same thing, except now you just got to remember that we're going the other way. So we're actually taking the register value in R0 and storing it at the address that's calculated based on the base address register and the offset. So it's the same thing, it's just going the other way, where you're storing values from the register into that memory location. So here I just put, you can take any program. This is just a main program from a lot of the examples. You'll see pretty similar stuff where they're taking variables and putting it on the stack. But since I was using pointers in this example, it'll store that value at that address based on the stack pointer here. So. So the address is on the stack, and so it's using that address to calculate an offset. It's like an array, basically. So, any question here? Should be pretty straightforward. So it's just showing you the different addressing modes. So here you have pre-indexing with write back. So it's going to take the stack pointer. It's going to take the stack pointer here, subtract 4, and then write that back into the stack pointer after storing the value of R2 at that address location. Right. So for loading constants into registers, like especially constants that are really large, it'll prefer, the assembler prefers to use a moven for whatever reason. So instead of writing LDR R0, this really large number here, the assembler for some reason has a tendency to choose a move negative, right? So instead of representing this large constant, it will take the ones complement and use that instead. And so it'll take a move negative of DC and it'll put that into R0. So this is just an interesting optimization that the assembler does. So don't be surprised when you use some constants in your program and you go to the assembly and you don't see it. You're like, what happened? Because it's just doing the negative, right? Some of these other instructions that are available are saturate. So these are all the same addition, subtraction operations, but it tries to saturate based on the bit mask that you provide in the second register. So it'll only do it up to that many bits, essentially. It'll saturate the value up to so many bits that you specify in register 2. So what that means is if the value goes above that bit position, then it'll truncate it and essentially just put the max value that can be represented in those many number of bits specified in register 2. And the add does the same thing, except it saturates the result of the addition. The subtraction does the same thing, except it saturates the result of the subtraction. QD add is interesting because it takes the double and then adds and then takes the saturation of that, and puts it into register 1. So and QD subtract does the same thing. It's just doubling the third register, subtracting it from the second, and then saturating that value, putting it into register 1. So back to control flow. So we had seen how branch operates earlier, where if you say branch label, it actually stores the address of that target label into PC and then branches. BL, BLX, and BLX do an additional operation where they take the program counter, save it into the link register before doing the branch, right? And CBZ, CBNZ are used for conditional operations, but I just wanted to go a little bit more into detail on how these conditional operations work. So most of the instructions in the ARM instruction set can be made conditional. So if you wanted to do a conditional add or a subtract, you could do that. You would just use a prefix or suffix, sorry. And you can look up a mnemonic actually from the table that follows. And this actually is a performance, it's meant to optimize performance because you can actually do branch prediction and things like that much better if you have the conditions. So this actually helps in that regard, which is why they have these conditional suffixes. So you already know equals, not equals. There's also CSHC, which is unsigned, higher, or same. It checks for the carry flag, high carry or lower order carry, where the C is 0 or 1. So you can You can branch based on whether the carry bit is set. And you can also do minus, where it's negative. This is usually never used. You usually use equals, not equals, greater than, less than, greater than or equals, less than or equals. But these are the sort of flags that are checked. And it's just using the flags from the current program status register to ensure whether the condition's met or not. And AL is almost never used because it's kind of pointless. You can always just say the instruction that you want to do, just add or subtract without. But they do have that mnemonic in there. So this was just, again, a reference to the CPSR flags. So now I'll talk a little bit about pipelining. So if you remember, we have three pieces to the instruction cycle. One was the fetch, where it fetches the instruction. Then the second one was decode, where it decodes the instruction, figures out what to do, and finally it executes it. So the important thing to remember about pipelining is that it does not improve your instruction execution time. It just increases the throughput of your code. So more instructions can be executed in parallel as opposed to taking time to fetch and decode, right? So here's an example. So if you had a bunch of operations where you have add, subtract, or, bitwise or, and then exclusive or, what it's going to do is it's going to fetch, decode, and then execute the first instruction for add. But while it's decoding the add instruction, it's also simultaneously going to start fetching the next instruction. And while it's executing the add instruction, it actually starts decoding the second instruction. And then finally, when you have or, it's by the time you're executing the first instruction, it's already fetching the third one. So this is sort of why I had mentioned earlier that the program counter is always pointing 2 instructions ahead, is because the execution is actually happening 2 steps ahead. Does this make sense? So in thumb mode, it's going to be plus 4 bytes because it's each instruction takes up 2 bytes, and for ARM mode, it's going to be plus 8 bytes because it's going to take up 4 bytes each for each instruction. So there's also problems associated with this. So what happens when there's a branch? And especially if it's a conditional branch, right? So a conditional branch actually helps in this regard because it actually reduces the number of branches that are possible, and it helps the branch predictor, which is actually part of hardware implementation on ARM, to reduce the number of branches, and therefore it can pipeline more amount of code and get more throughput. So every time you do a branch to a fresh location, you just say branch to this address, it has to flush the pipeline. So if you can reduce the number of branches, it's going to reduce the number of flushes in the pipeline, and therefore you're going to get more throughput. So instructions, again, are dependent heavily in this case on the previous instructions. So this is called data dependency. And what happens if there are interrupts in the middle of the pipeline? I'll talk a little bit more about interrupts later, but interrupts are literally what interrupt your program flow, right? And then start executing some other piece of code. So when an interrupt occurs, whether it's in the beginning, middle, or end of a cycle, right, it's going to finish whatever it started. If it's executing an instruction, it finishes that, and then it flushes the pipeline and jumps to the interrupt. Does that make sense? So we're going to see this a little bit later. So how the code is actually optimized is very heavily dependent on the actual implementation of the ARM chip on the hardware. So it's dependent on the processor, it's dependent on the compiler.
Is data dependency visible to the assembly language programmer?
No, but it's it's available to the program design, right? So the person who's writing the code can write their code in such a way that it's pipeline friendly. So
does the decode phase care about the contents of things? Like if you're using R2 as a base register,
yep.
Does the decode phase care what's in R2 or just that you specified R2?
I think it's going to...
The currently executing one is going to change R2. The currently executing is going to change R2.
Right.
Does the decode phase of the next instruction, does it care what's in R2 at that point, or is it going to wait until it executes and then care about what's in R2?
That's a good question. I believe it's going to not care about R2. So ARM chip doesn't have hardware intelligence, I guess, if you will, to figure that out. So we have to be careful when we're pipelining also to make sure, and that's the reason I brought up interrupts, right? So, so interrupts is a good example where you have changed the values in the register, interrupt occurs, some other piece of code starts running, but what happens to the values in R2? So I'll go to a little bit more detail on interrupts later. But that's a very good question.
But if you're writing an application level program, interrupts are somebody else's problem.
Right.
You want to make sure that you're not, when you're in certain sequences, you're not messing things up. That's why I was just wondering if it's for an application level programmer.
Right. I believe it compromises data safety, if you will, right? So you can't be sure of what value is in that register. That's why we have to kind of we have synchronization deadlock problems still, even on ARM. So, yep. I hope that sort of answers, but I'll have to look into more detail on how the ARM hardware does that. So, but most of the time, that's why it's very dependent on the processor. It's dependent on the compiler, so things can change depending on how the implementation is defined. And a lot of the ARM manuals you'll see is they actually use implementation define as sort of a throwaway to say, just check with the vendors. So other ways of branching, we had looked at the branch instructions, but there's also other ways we can do it. You saw popping a value from the stack into PC also does a branch. You can also, so anytime you basically write to the PC, it causes a branch to occur. So here you can do LDR with PC, and an offset, so you can jump to a value. Again, this will flush the pipeline, and so it'll start over from the new offset that you've given. And the value written has to be aligned for the mode that it's in. So if you're in thumb mode, that address has to be aligned to half words versus ARM mode where it has to be aligned for full words, 32 bits. So earlier processors actually used to have prefetch, and this is sort of the reason why they stuck with the convention. So ARM version 4 and earlier, the program counter always pointed 2 instructions ahead for the reason of implementing pipelining. And so even to this day, they've continued with that sort of convention, if you will. And I just thought I'd put that in there. So here's an example. So where do you guys think, after executing the instruction that's been highlighted, where do you think the next instruction to be executed will be? Yep, that's right. It's going to be this guy right here. This guy right here is going to be the next instruction to be executed. So let's look at why. So the PC at this point is pointing to 2 instructions ahead, right, when it's executing this guy. But it's going to say load LDR PC plus 4. So PC is actually pointing here, right? So it's going to say take the memory contents of the program counter, which is this guy, add 4, which is this guy, right? And load that address's contents into PC, which is, so it loads this address into PC and causes a branch to this target. Does that make sense? So this is the this is sort of like if you had a lookup table for jump targets, right? You could use this sort of, and we'll see this being used in something called the interrupt vector table. So when you wire your interrupts to say, this is the code I want you to run, you'll see a bunch of these instructions, LDR, PC, PC, 100, you know, and you'll see that later. So this is very important. So now we come to the one, or actually two instructions to rule them all. So we have LDM and STM actually stand for load multiple, store multiple. And this allows you to do consecutive memory and register accesses. So you can load a lot of things in one instruction, again, for code size. Right? It's actually also optimized because if you use these, you can tell the cache, the TLB cache that sits in between the memory and your processor, hey, you know, I'm going to do consecutive accesses. Why don't you just start caching all these values, you know? And so then it doesn't have to go to the DRAM. It can just go to the cache, pick up those values, and start using them right away. So it's actually a performance optimization again. So this is how load multiple and store multiples work. So load multiples have different modes. So you can say start at one address, go up to this address by you know, incrementing by 4 every time. Or you can say start at the top, go down below 4 at a time. You know, so increment after, decrement after are two different modes essentially. So if you use LDM-IA, you can't use STM-DA, and vice versa. So the start addresses and the end addresses differ a lot. So between these 4, but there are mnemonics that ARM provides. For example, for doing stack operations, you would use LDMFD and STMFD. What that means is it knows the mode that the stack operates in, right? And so it's going to use this to mean LDM-IA when you're doing LDMFD and STM-DB when you're using STMFD. So we'll look at an example of this. So earlier, we were using push and pop instructions for the stack. But now we're going to start using the LDM and STM instructions to do the same thing. So generally stacks are either ascending stacks or descending stacks. So generally it's usually a descending stack where the stack grows to lower memory addresses from a higher memory address. And so this is why the most common two instructions that you'll probably use are going to be LDMFD and STMFD. And those are just mnemonics for LDMIA and STMDB. So these are the pairs that you would use. So you can use, these two are actually descending stacks, and these two are for incrementing stacks. But it's just a matter of where the stack pointer starts, whether it starts on an empty space or in filled up space. So let's look at one of the examples here. So we have STMDB. So this would be the same as writing STMFD. But now what you're trying to say is stack pointer, and here's an example of pre-index with writeback. So this is actually special. You say after you've used the stack pointer, update it to the latest value. So it's going to write the, after it stores these registers on the stack, it updates the stack pointer to point to, as you'll see, the last value that was written to. So our stack pointer starts off pointing to here, 8018. And we have R3, R4, R5, R7 that we want to put onto the stack. So it's going to start off at, if you refer to your table again, it's going to start off at x minus 4n, right? That's the start address. So that means it's going to take, there's four elements. So we're going to take 4 times 4 is 16, and we're going to take 8018, subtract, this is all hex again, subtract 16, and then we're going to start off at 8008. So we store the first value, which is register of R3. The next it calculates is, and it goes all the way up to x minus 4, which is, so 8018 means it stops 4 bytes before. So R3, R4, R5, R7 get put into the slots above the empty slot. So your stack pointer generally points to an empty slot. If you remember from the push and pop operations, it points to the, the stack pointer points to the top element of the stack. So that's going to be a non-empty space generally. So once you have updated the stack, you want to load it back into the registers, sort of the in the epilogue. So now the stack pointer, if you remember here, gets updated to 8008, which is actually the first element that it started off with. So this is STMDB. So once we do LDMIA, it's already 8008. It's going to start loading the values back from the stack into the registers. And it again stops at 8014, and it puts that into R7. And then the stack pointer gets updated to back to 8018. So when we had the store multiple descending, it actually put the stack pointer at where the first register was stored at. So this is important. So if you reference the stack pointer after this instruction, it will point to the first element that was put on the stack, which is at the bottom of the stack. Actually, this is the top of the stack. It's just pointing to 8008. So if you see, this is increasing memory addresses downwards. So the stack is actually going to grow upwards. So we're going to have R7 is actually going to go to the bottom of the stack, and R3 is going to go to the top of the stack. So even though it starts storing them in the reverse order, this is what makes it confusing. So even though it starts storing them from top to bottom of the stack, right, the stack is actually still following the convention of going from bottom to top, because the addresses are decreasing going up. Does that make sense? So that's why they've provided the LDMFD and STMFD, and that sort of takes care of the addressing for you. And this is just the way that their hardware implements it. So we have to be careful when we use the stack pointer after using either of these instructions. So if you don't understand the stack operation yet, don't worry, because I'll get into more details when we cover calling conventions on how the stack works. So.
Does the SP get put back to 8018?
Yes. So the stack pointer gets updated back to 8018. So generally what you would do is when the function is called, you want to store the registers according to calling convention into the stack. And when that happens, you're using STMDB, which is the slide further to this. And the stack pointer ends up pointing to the top element of the stack, but the order it puts it in is reverse. And so you can still use the stack pointer after this, right, and push more things on, but after you're done with your method, then you want to put the register values back, and you would use the LDMIA as the mnemonic for loading them back into the registers. Because otherwise, what will happen is if you use STM or LDMDB or LDM ID, sorry. So it's going to start at one address prior. So it's going to start at 8004 and try to load values back into the register. So you just have to be careful, which is why they sort of give you these mnemonics. So fully descending is generally for stack operations that are descending. And you could use full ascending if your stack is going towards increasing memory, and so on. So here it would be LDM DA and then STM IV. So that's the difference. So here's an example of a function prologue and epilogue, is what it's called. So the prologue actually stores the registers that are going to be messed with in this method onto the stack. So you see they're using STMDB. And then they actually do their work, mess up all the registers, and then they want to load them back. So they use LDMIA to load them back. So when you specify here, they're using link register to store the link register on the stack. And once they're done, they actually put it back into PC directly. And so that causes the branch to occur.
Application 8362, that wide load, that one. What value does PC have there? Is it the current instruction plus 4 or plus 8? Because you've got a wide instruction followed by 2 narrows.
Yeah, so the wide is actually for this guy, this instruction itself. So it's saying the instruction is encoded 32 bits.
Right.
Right. And all it's saying is take the value of PC.
I'm wondering what is the value of PC at that point?
So it's going to be pointing to this guy.
Okay.
And it's going to add 52, which is going to, so depending on 8366 or 8368, sorry,
okay.
Plus 52, which is 8398. Yeah, 52 decimal.
Yeah.
This is in hex, so you have to convert. But this is actually pointing to the libc library, which is actually located down. Actually, this is a jump table, so it's probably loading it's loading the memory contents up. So it's loading this address. Does that make sense? So it's taking PC plus 52, which is this guy, the memory contents of this, interesting, and storing that into R9. Okay. So it's going to store 4D0C into R9. And here it's going to store 44F9, actually no, PC plus 52, 8398, which is this value. It's going to store this value in R9, and I'm guessing this value into R5. That's what it's doing. Does that make sense?
Yeah, I'm just doing the arithmetic there.
Okay.
To get 8398, the PC value is 8364, I guess.
PC value here is going to be 8364. Oh.
You're just doing the arithmetic, yeah.
Yes, that's right. So why is it 8398? So this is on the emulator again. So I'm thinking this is an emulator artifact. But on the actual system, it would point 2 instructions ahead. So, okay. I'll have to do that out. I'll get back to you on that. So actually that brings up a great point. So now we can go into switching modes between ARM and thumb. So when we say ARM mode, everything is 32 bits no matter what. But when we say thumb, it means it's either 16 bits or 32 bits. And you get this sort of mixed assembly that you saw earlier, where you have 32-bit instructions mixed with 16-bit. And generally, all the examples I have here are all in thumb mode, so just keep that in mind. And a processor in thumb mode can enter ARM when it uses any of these branch instructions or the LDR on the PC. So essentially, whenever you're doing a branch, depending on what mode that you've set, it can change the mode from thumb and enter ARM, and vice versa. If you have a processor in ARM and you want to enter thumb, you can use any of these instructions and it switches the mode because some of these instructions are only available in 32-bit depending on the encoding that you end up using. So the thumb2 instruction set means 16-bit, 32-bit instructions are mixed, but it still means it's running in thumb mode always. The compiler option to actually mix ARM mode and thumb mode instructions, which mean have 32-bit instructions as well as 16 and 32 mixed, is going to be called mthumb interwork. I'll be honest, I haven't delved too deeply into this inner work, but the default is to turn that option off. And it confuses the heck out of people anyway. So how can we tell the difference whether we're in 16-bit or 30, whether we're in thumb mode or not? This was asked by Zeno. So the ATPCS manual, at least for ARM, this is also included in your reference manual in the VM. You can look it up, but it says that it checks the least significant bit of the actual address, so which makes the address odd, actually, because if it's set, it means the instructions are interpreted as thumb2. And if the bit is not set, that means it's interpreted as ARM. So if you want to jump to an address containing a mix of 16 and 32-bit instructions, you want to make sure that you set that least significant bit. And this will become important later on in the hijack lab, where we try and do our own control flow hijack. So just keep that in mind. So how does the processor itself differentiate between thumb mode, in thumb mode between 16-bit and 32-bit instruction? So the ARM processor is always, it's in thumb mode, and it has to figure out whether this instruction that I have to interpret is going to be 16 bits long or whether it's going to be 32 bits long. So what it does is it actually looks at the encoding. So bits 11 through 15 of it reads half words at a time, and it checks bits 11 through 15 to see if it's any of the following. And if it is, then it knows that it's the first half word of actually a 32-bit instruction. Otherwise, it interprets it as a 16-bit instruction. So it checks, so the processor is just fetching 16 bits at a time. It checks the bits 11 through 15 of the half word it's pulled. And if it's any of these values, then it knows there's another half word it needs to complete the instruction. Otherwise, it says, I've got my half word, I'm just going to execute it. So now we'll get into the ARM thumb procedure call standard. This is, again, I referred to this earlier. It's part of your reference material in your VM. It's also available on my transfer folder. But the ARM thumb procedure call standard basically defines how subroutines are handled and how they're called, and what registers need to be saved and what registers you don't need to worry about, basically. So there's something called caller saved registers, where the method that's doing the calling of another method has to save some registers because the called method is going to modify those registers. So those are called caller saved registers. So generally, the caller has to save R0 through R3. If you remember, I mentioned that you pass arguments to methods using these registers. R0, R1, R2, R3 are used for argument passing to methods. And so the caller has to save those registers if it wants them back. Because R0 for sure, if the calling method, called method has a return value, it's going to be overwritten. And so it needs to save R0 through R3 before calling the method. The callee saved registers are the registers that need to be saved by the function being called. And so in this case, the called subroutine must preserve the contents of R4 through R11. And usually it's saved in the stack. And this is what you see in the function prolog that we saw earlier, the STMDB, LDMIA. You saw some of these registers getting saved to the stack. And it's actually the ARM thumb procedure call standard calling convention. So the reason R4 through R11 must be saved is because the caller, the function doing the calling of the other method, will need those values back once the function is returned. And so if the called method goes in and changes those, then it has to restore them to the original state before returning to the calling method. So what happens during interrupts to these registers? Anybody have an idea?
I know the answer to that.
Okay, go for it.
Depending which one it is, there are various numbers of bank registers. So
Exactly.
in some of them, it banks most of the registers in some of the banks, just a couple of them. But in particular, it always banks the program counter and the link register. And I don't know about the stack pointer.
Yep, exactly. So we'll cover this when we get to interrupts, but so each mode has its own set of banked registers, and what a banked register means is it has its own memories, actual flip-flops, I guess. That's how registers are implemented. So it'll have its own registers that are independent of the mode that you're in. So if user mode has R0 through R11, FIQ has a set of banked registers which go from like R4 through R10 maybe. So it has its own set of registers, and those registers are essentially can be used in the new mode without affecting the original mode's registers. So this is the ARM Thumb procedure call standard used for registers. So as I've mentioned, R0, R1, R2, R3 are used for arguments to the called subroutine. R4 through R11 can be used as variables in the called subroutine. R12, R13, R14, R15 are special registers. R12 is actually scratch, what you refer to as RSI on x86. But R13, 14, 15 is our special registers, and Galen had mentioned whenever there's an interrupt or a mode change, you'll have the program counter, link register, stack pointer, and these special registers banked out as well. So you'll be able to write to PC, but actually PC is not going to be banked because it's only one program counter, but only link register and stack pointer are going to be banked up. So we'll see that. So just to show you graphically which ones are caller saved and which ones are callee saved, R0 through 3 are caller saved, and R4 through R11 is going to be callee saved. The frame pointer is neither mandated nor precluded from being used. So it's essentially up to the implementer to decide whether they want to save the frame pointer, which is R11, or not. But the standard doesn't specify, whether you have to save it or not. Usually R4 through R7 is used in thumb mode for your frame pointer. Generally, we've seen R7 being used. If you remember, stack pointer gets saved into R7. Otherwise, if you're in ARM mode, which we haven't seen any examples of yet, R11 would have been used as the frame pointer. It's essentially the stack save of the stack pointer when you start the new method. So what does this look like in action? So you have 3 methods here that I'll go through. The main, which calls method 1, and method 1 calls 0 and 2, and then method 2 just prints a statement. And so, so we'll look at how this stacks up. So we're going to have, starting off, we're going to start with the main's frame, right? The main method's frame. And that'll actually look like this. So the memory is increasing this way, and actually the stack should be growing downwards, right? So that's what I'm showing here. So you're going to have in the main, you're going to have any local variables, which in our case is nothing. Look, there's no variables, but if you did have variables there, this is where they would be saved. Then you would have the color saved registers. Wants to name what those are? It's going to be R0 through R3, right? Because those are going to be used for arguments to the called method, which is going to be 1. So, and then you set the arguments to 1, and you call 1. So what happens is a branch with link occurs when you call 1. So if you look at the assembly code that's generated, it'll actually have a BL or BLX instruction to 1. And so the program counter gets updated with a new value to the address of 1. Now, ARM has switched over and is now executing at the new program counter. So the callee saved registers have to be pushed onto the stack because that's the convention. And you use STM fully descending or STMDB, right, which are the same. And you say stack pointer with registers along with the link register. So generally, the link register also gets saved on the stack. And we will see why this is helpful for attackers. So, yes. And once the link register gets saved, then the callee has its own saved registers that it can put on the stack, which we mentioned up here. So all these registers are going to be in here. So now the stack keeps growing. We have local variables now in 1, if there are any. So there is no local variables here, but if you had local variables, that's where they would get saved if you ran out of space with registers. And then now there's a call to 2, if you remember, in 1. So since 1 gets calls 2, it puts the arguments to 2 and saves the R0 through R3 if it needs to on the stack. And then the branch with link occurs to 2 now. And so these arguments to 2 are still on the stack. And now the frame gets updated. So these arrows you can think of as sort of defining the boundaries of the frame. So now the link register will contain the PC of 1, but on the stack you still have the link register for method 1, which points to main, right? So as you can see, this is very similar to x86, except that the frame pointer isn't used as heavily, but and the stack pointer, as we saw, was being updated using STMFD or LDMFD, which stands for STMDB or LDMIA. And despite the return address being saved in the link register, most often it's put on the stack. And so you can actually write onto the stack. And if you're able to write to the stack, then you can control the PC in this way. This will help you in the hijack lab. Okay. Just want to put that in there. So now we'll talk about modes. So as I mentioned earlier, ARM runs in different modes. We've been talking primarily about the user mode so far, which is where all the userland programs run. The other mode that we looked at briefly was the supervisor mode, which was activated when we called the SWI, or the software interrupt instruction. We can also use an SVC, which is also an instruction that does the same thing. Then you have 2 interrupts modes, which are called FIQ and IRQ. IRQ is a normal interrupt, and FIQ is a fast interrupt. The fast interrupt essentially has more banked registers, so you don't have to waste time saving stuff to the stack like we saw earlier. So you can just start using those registers right away, and so it kind of makes it fast, I guess. That's why it's called fast interrupt. The IRQ has less banked registers, and so it's slower. You have to save all the registers into the stack, then use them, and restore it. Finally, you have abort. and undefined and system. So an abort can occur when you have page faults and things like that, or the undefined occurs when it accesses an illegal instruction. So the processor doesn't recognize the instruction, so it can go into undefined mode. And finally, system is similar to supervisor. I haven't seen it really being used outside of supervisor. So that's what this slide talks about. So a user is normal program execution mode. FIQ is used for handling high priority fast interrupts. IRQ is used for handling low priority normal interrupts. Supervisor actually is the mode that's entered into when you first reset the power. So when you power on a board, first mode it's going to go into is the supervisor mode. And if you look at the vector table, which I'll talk about more later, the way to handle a supervisor mode interrupt or supervisor exception mode is to run the handler that's located in that interrupt vector table for supervisor. And all that does is it starts executing a specific address. So there's an LDR PC plus some offset, and it just starts executing. And this is why we saw earlier in our U-boot example, right? So it just starts executing the code at a specific address. And that's because there's a interrupt wired up for a supervisor that actually tells it to start executing instructions at a specific PC location. Okay. So system, again, is a privileged mode, just like it has the same registers as user mode does and supervisor. So this is what the bank registers would look like. So what the bank register does is, in user mode, we had R0 through R15, followed by the CPSR. Now these new exception modes, like the FIQ interrupt mode and the IRQ interrupt mode, introduce these banked registers, which are physically separate in hardware from these registers. So you can actually start writing stuff in here in this mode without affecting values stored in registers in the user or system mode. Does that make sense? And similarly, the IRQ mode has just the stack pointer and the link register that's banked, and supervisor mode does the same thing. So as you saw in a kernel, I guess, which runs in supervisor mode, you would still need to save these registers because those aren't banked, right? So you need to preserve the userland registers. You can still access userland registers in supervisor mode. And same thing in IRQ mode. You can access these registers too, but except for R8 through R14. And if you need these registers to in your FIQ mode, you need to put them on the stack somewhere and tell FIQ mode, this is where my stack is, go look at these register values that I've saved. So if you remember, the CPSR has a mode section. And so this is what the encoding looks like for that mode in the CPSR. So you can actually see which mode you're in by reading the CPSR. And there are special instructions to do that. You can't use load LDR, STR. I'll go that. So the user is 10,000. Actually, this is all binary. So. And the privilege level actually is opposite to what you would think of as rings in x86. So it's actually the higher the number on the privilege level, the more privileged it is. So the hypervisor mode apparently has the highest privilege level, which is PL2. The monitor mode, which we'll talk about a little bit more, I touched on it briefly, it's called trust zone, where you have this separate area of memory that you can use. That's at privilege level 1, and it's actually at the same privilege level as the FIQ, IRQ, supervisor, only the user mode is PL0. So PL0, this is the lowest privilege level that's available on the ARM. And then I also have on the rightmost column what instructions trigger the switch to these modes. So if there's a interrupt that's been wired, either via hardware or via software, you can be in either FIQ or IRQ mode. So if you actually have a wired line that's hooked into some pin, and you have a memory I/O register that accesses those pins, you can actually set a mask and enable or disable these FIQs and IRQs. So the FIQ, IRQ are most primarily hardware-driven interrupts. So you can physically interrupt the processor while it's doing some work. The supervisor mode, which we've seen, is enabled by using the SVC or the SWI instruction, which is software interrupt or supervisor call. If you had trust zone on the ARM board, that would be enabled using the SMC, which is secure monitor call instruction. So once you say SMC, it either switches to monitor mode or back from it runs monitor code, and the monitor code can decide to run the secure code, or it can decide to switch back. Abort is happens when you have a data or prefetch abort or misaligned memory access, and you can enable or disable these interrupts again. Finally, you have the hypervisor. The Cortex A15 processor, which has been shipped out to all the vendors. It's still not on mobile phones today, but it has hardware extensions for virtualization, and it has large physical address extensions, LPAE. So those chipsets will have the hypervisor mode or hypervisor mode enabled. And so it depends on the vendor's implementation again. But there's a call called HVC, which is the hypervisor call, to enable the hypervisor mode on the processor. Finally, you have undefined and system. Undefined occurs when you have an illegal instruction that the chip can't figure out the opcode is illegal or something. So it goes into this undefined mode. So again, the mode changing instructions are SVC or SWI for supervisor, SMC for secure monitor call, and HVC for hypervisor. So primarily, the ones you'll be seeing are the SVC or the SWI. The IRQ and FIQs are actually enabled using hardware, and you actually set a register with a mask to say whenever this pin goes high, jump into FIQ or IRQ mode. And unfortunately, since we're running the emulator, I can't show that to you on hardware, but you'll just have to take my word for it. So if you remember, we had covered the banked registers. So an additional register that I did tell you about is the SPSR. So the SPSR is a separate register that's available for each mode. So one mode's SPSR can't be changed by another mode's SPSR. But what essentially happens when you make these calls, like the SVC, or whenever an FIQ interrupt occurs or an IRQ interrupt occurs, the ARM chip automatically puts the contents of the CPSR and saves it into the SPSR. So CPSR stands for Current Program Status Register. SPSR stands for Saved Program Status Register. So all it's going to do is it's going to copy your mode, the last mode you were in, your flags, and whether it's ARM mode, thumb mode, all those, and whether IRQs and FIQs are enabled or not, and put those into the SPSR for you. And then it starts executing whatever's in PC, whatever's in the interrupt vector table, it starts executing there in that mode. So when we want to return from our mode back to user mode or back to supervisor mode, right, or whatever mode we're coming from, it's going to be saved in the SPSR. And when we copy the link register back into PC, we can't restore the SPSR at the same time back into CPSR, because if you write the SPSR back into CPSR, the mode's going to change, and your next instruction is not going to be executed. It actually causes the mode to change, and it's going to go back to your interrupt vector table. So there has to be a way of restoring CPSR as well as the link register back into PC all at the same time. And this is the instruction that actually does that. So if you remember, I said the MoveS PCLR instruction is special because this S actually stands for the CPSR update. So it copies the link register back into PC from whatever mode you're operating in, as well as simultaneously it copies the SPSR back into the CPSR. So it does those two things all in one instruction. Does that make sense? So this will actually restore the mode you're in and restore the link register or the PC, the program counter that you were in that mode that you had left from. And you all remember the software interrupt exception from Hello World that we looked at. So there are some other special instructions, just like MoveS PCLR. You could also do a sub-S PCLR, and it also does the same copying of SPSR back into CPSR while subtracting some offset value from the link register and putting that into the PC. So this is very useful when you're returning to user or system mode from exception handlers or interrupt modes. So how can we actually write to the CPSR if we had to? So you have these two instructions, MSR and MRS. The way I remember it is S is special, R is register. So this is the destination and this is the source. So you're going to move into the special register, which is CPSR in this case, a value that's stored in the core register, and that can be R0 through R11, right? And similarly, MRS is the other way around, where you want to take a value in the special register and save it to a core register. And so the way you'd use it is MSR, CPSR, and then the register, or MRS, R0, and then the CPSR. So this is also confusing. If you remember, I'd said the destination always comes first. So here, if you notice, the two have been switched, even though you're only operating on that CPSR. So it get a little confusing. Another register that I haven't covered yet is called a coprocessor register, which is CP15. There's actually CP13, 14, 15. I won't go into that in this class in much detail, but all you need to know is that within there's a coprocessor is actually a separate processor, I guess, and it has a set of its own registers that control system-wide settings. And this is mostly used when you have multi-processor systems. So you can actually take multiple ARM chips and create some sort of a parallel computer, if you will. And essentially, this controls system-wide settings. So if you wanted to enable, disable interrupts across the board, if you wanted to set the endianness, it allows you to do that for data, not for instructions, like I had mentioned earlier. And it also, for exceptions, it sets whether you want to handle the exceptions in ARM mode or thumb mode globally across all processors, things like that. And it actually also has the base address for an exception vector table. So I'll get into that a little bit more. So if you remember, all these exceptions can occur at any point during the processor's instruction cycle, right? So what this does is the vector table actually has the address to jump to start executing in that new mode. So when it first jumps to that new mode, it looks up the PC that it needs to jump to from this exception vector table, and then jumps to that piece of code and starts executing there. So the SCTLR is actually, there are two default values for this exception vector table. It's generally and most likely always located at 0x0. So, and if you remember, that's DDR SDRAM from our memory map. And so the exception vector table is always at 0. And you're going to have the first few segments of memory reserved for this exception vector table. And sometimes, though, the only other option is hex FFFF0000. And there's a single bit that changes whether you want the exception vector table to be located at the beginning of memory or at this new address, FFFF0000. I don't know why they did it that way, but that's the way ARM has designed it. So, and finally, for the Cortex-R profile, and this only applies to the Cortex-R profile, so these CP15 and SCTLR registers will differ across the different profile and different architectures. And so on the Cortex-R profile, if you remember, we had a divide instruction, signed divide and unsigned divide. There's a bit in the SCTLR that actually sets whether you want to throw an exception when there's a divide by 0 or it generates a 0 after you divide. And that's available on the Cortex-R profile. There's also an IE. This is for instruction endianness. And this is also Cortex-R only. And all that says is, the ARM manual says it's implementation defined, which means TI or whoever is making the board sets that bit and says, my chip is going to use instructions in little endian or big endian. And you can do nothing about it. So it's a read-only bit, and you can't set it, but it's something that's there for you to use. All right, so I'd like to stop here and ask if there are any questions so far about exceptions, interrupts,